Okay, so before we have done resistors in series, now we're moving on to resistors in parallel, which is almost the opposite to what happens in series. And you have also done this in grade 9, so you should go and look at your grade 9 work, and that will make it much easier for you to understand this here. Right, so it's on page 140 of your textbook, and we're going to go through what happens to each of the three things: resistance, current, and voltage in a parallel circuit. Now, first of all, you need to figure out when a circuit is actually in parallel. And remember, just the way we said how you do it in series, for parallel you do the same thing. So every time you're trying to find out if a circuit is series or parallel, you ignore the voltmeters. You ignore the voltmeters completely, because we know all voltmeters will be in parallel, whether it's a parallel circuit or not. So you ignore the voltmeters and you only focus on the light bulbs and the resistors. If the light bulbs and resistors are next to each other, it's a series circuit. If the light bulbs or resistors are in branches, then it's a parallel circuit. So if you go to this diagram on page 140 of your textbook, can you see that you have many voltmeters? You have VT, V1, V2, V3, VP. There's many voltmeters and they're all in parallel. But that doesn't mean necessarily it's a parallel circuit. But if you look at the resistors, you'll see that you have R1, R2, R3. Since those one are in branches, they are not next to each other, they are in branches, which means this is a parallel circuit. So you will always look at the bulbs or the resistors to see if the circuit is series or parallel. Right, now let's start off with resistance, and let's see what resistance, how you calculate resistance in parallel. Now, remember we said another word for total resistance is effective or equivalent resistance, and the way that you calculate resistance in parallel is very different to series, and it's actually using this formula here, which is on your data sheet. Now the formula is 1 over Rp, and P means resistance in parallel, is equals to 1 over R1 plus 1 over R2 plus 1 over R3, etc. for however many resistors you have. Now, if you look at this formula, can you see that we're using all of the resistors? We're using R1, R2, R3, but we are saying 1 over it. So you're going to say 1 over that resistance. Okay. And that will give you 1 over Rp. And later on we'll see in calculations how you have to change this to actually get the answer that you want. Now, there are many ways to calculate resistance in parallel. If you go to your page 140 in your textbook, you'll see that sometimes they even use this formula, Rp is equals to R over N. They also use this one, Rp is equals to R1 times R2 over R1 plus R2. Now, these kind of formulas are very limited. You can only use it in certain cases. So this is why I prefer to show you this formula, because this formula can be used in all cases. It's not limited to certain things. You can use it every single time and you will get the correct answer if you use it properly. Those other formulas, you can only use it in certain cases. So instead of confusing you with many formulas, I just want you to use this one formula. It will make your life much more simple. Right, now remember in series, we said that the more resistors you add in series, the greater the resistance will be. Now, in a parallel circuit, it's actually the opposite. The more resistors you add in parallel, the lower the total resistors will be. Which means, even though you can have many resistors, even if you keep adding and adding resistors, it actually makes the resistance lower. So, adding more resistance makes the total resistance lower. So, whatever happens in series, the opposite happens in parallel. So, just remember, the more resistors you add in parallel, the lower the total resistance will be. Right, let's move on to current in parallel. Now, we said in series, current is the same everywhere, which is the total current. Now, in parallel, it is the opposite. Current is divided in parallel, and if you add all of the current, then you will get the total current. And since current is divided in a parallel circuit, we call them current dividers. Okay, so the current will be divided in a circuit, and if you add all of the current in the circuit, it will give you total current. So it's I total is equals to I1 plus I2 plus I3, etc. So all of the currents added together will give you total current. Now, even though current is divided in parallel, it does not mean it is divided equally. In fact, most of the time it is not divided equally. So don't assume that if it's divided, each light bulb or resistor will have equal current. They will not have equal current. And since they will not have equal current, we have this formula, which is called the ratio formula for current in parallel, also called the current divider formula. And this formula gives you the current in parallel for a certain resistor or light bulb. So it gives you specific current for a specific light bulb or resistor to find out how much current each light bulb actually has. So let's see what this formula is. It's IR1 is equals to R parallel over R1 times I total. Now R1 is not necessarily the first resistor. It can be used for any resistor. And this is the specific current that you are trying to work out. So it's the specific current for a specific light bulb or resistance. Okay, then you have R parallel. Now R parallel is the total resistance in parallel, which you get from this formula here, resistance in parallel, divided by R1, and R1 is the specific resistance of what you are trying to find out. So the specific current that you're trying to find out is R1, and R1 is also specific resistance of that light bulb or resistor. It's not the total one. R parallel is total, R1 is specific. Then you multiply this by I total, and this current here is the total current in the entire circuit, which you get by adding up all of the currents. Okay, now we know that the current is not divided equally, but remember from before we said that current and resistance are inversely proportional to each other, which means whatever happens to current, the opposite happens to resistance and vice versa. So if you have a light bulb with low current, it means resistance will be high because the opposite happens. If you have a light bulb with high current, it means the resistance will be low. So if you have many bulbs or light bulbs or resistors in a circuit, and you know the one has a high resistance, which means you should expect a low current for that one, and if you have one that has a low resistance, you should expect a high current for that one. Okay, right, let's move on to the last thing, which is voltage. And we said for voltage is the opposite. In a series circuit it's divided, but in a parallel circuit voltage is the same everywhere, which is also equal to the total voltage, and we know the total voltage is the voltage across the cell or battery. Right, now sometimes you can have series and parallel together in one, which means that only the parallel part of the voltage will be the same everywhere. But if you only have a parallel circuit alone with nothing in series, then the voltage will actually equal to the total voltage, and all of the voltages will be the same everywhere. Okay, right, let's just recap. So for resistors in parallel, the more resistors you add, the lower the resistance will be, and you calculate it using this formula here. For current in parallel, current is divided, and if you add all the currents, you'll get total current. And if you want specific current through a light bulb or resistor, you use this formula here, and current is inversely proportional to resistance. And then for voltage, it will be the same everywhere, which is equal to the total voltage if there are no other resistors in series.